Hello, everyone. I'm here to go over lesson 6.5, translating between definite integrals and Riemann sums. So our goal in this lesson is to be able to do problems C and D, which are AP questions on how to translate the limit of a Riemann sum, which represents a definite integral, into one of the definite integrals and vice versa. So we'll start from the beginning. We'll go back to the do now. So let's do that. Okay, let's take a look at this example. The definite integral from 1 to 2 of x plus 1 with respect to x. Now, remember, we really don't need to use a calculator to evaluate this definite integral, because if we just sketch x plus 1, y equals x plus 1, which has a y-intercept of 1 and an x-intercept of -1. Okay, so this is the graph of y equals x plus 1. We're asked to find the total net area from 1 to 2. The area of this region, which is the area of a trapezoid above the x-axis. So we could easily do that by hand, but we could also use our calculator to compute this. But if we wanted to represent this Riemann sum as a Riemann sum for this definite integral, what we're going to do is we're going to use right RAM. Okay, we're going to use this as an example. So our discussion will all be in right rectangle approximation method. So the width of each subinterval, if we subdivide the interval from 1 to 2 into n subintervals of equal width, well, a is 1 and b is 2. These are the limits of integration. So the width of each subinterval is 1 over n. And to get the actual subdivisions, we would start with 1 and add 1 over n. So that would be 1 plus 1 over n. Let me just write down. And then we would go from 1 plus 1 over n and add another 1 over n, which is 1 plus 2 over n. And the next subinterval would be 1 plus 2 over n, and we add another 1 over n, which is 1 plus 3 over n, and so forth. And we would keep going until we get to 2, which would be, I guess, 1 plus n over n. So the right endpoint in each of these subintervals would be 1 plus 1 over n, 1 plus 2 over n, 1 plus 3 over n, 1 plus 4 over n, and the last one would be 1 plus n over n, which would give us our 2. And if this is when k is 1, and when k is 2, and when k is 3, and when k is 4, we could represent the right endpoint in the kth subinterval in terms of k as 1 plus k over n. All right, so if f of x, which is the integrand, is 1x plus 1, f of x sub k would be f of x sub k plus 1. But f of x sub k, as we have up here, is just 1 plus k over n. Now, this is our x sub k, so I will highlight this in green. And add another one, so that would be 2 plus k over n. So the height of the rectangle in the kth subinterval would be 2 plus k over n. The Riemann sum would be the summation from k equals 1 to n, and we would add up the rectangles in the form of a height, which is 2 plus k over n. This is the height of the kth rectangle. And the width of the kth rectangle is delta x, which is 1 over n. And if we want to complete this as a definite integral, the only thing we need to append is the limit in front of it. So it's the limit as n increases without bound of the Riemann sum. And this would represent the definite integral from 1 to 2 of x plus 1 dx. All right, so working backwards, notice that delta x is factored out. So I'm going to highlight that. This is our delta x. And the f of x sub k is really what's in this parentheses. So this represents the function at the kth x value, right endpoint. All right, but to get x sub k, this is the key. If you look above, x sub k in our problem was 1 plus k over n. And if we break that down, 1 was a, and the delta x was 1 over n times k. So the right endpoint in the kth subinterval could always be represented as a plus delta x times k. Okay. All right, so this is the key. We always begin, first we have to identify a and b. Okay, and then once we do that, we could find our delta x. Once we get our delta x, we can identify our x sub k as a plus k times the delta x. All right, now this is very important because everything stems from x sub k. That's the first thing we had to find in our analysis. And from there, we can find f of x sub k, and which will give us our f of x, and then finally our Riemann sum. And we could go back to our translation. So let's take a look at A. Okay, 2A. We'll do that together. So in this problem, let's identify A and B. A is 1 and B is 3. Okay, so our delta x here is 3 minus 1 over n, which is 2 over n. Okay, that's fine. Now, x sub k, by the formula, is a plus k delta x. So when we substitute, x sub k is 1 plus k times 2 over n. Our f of x sub k is the integrand. This is f of x sub k. Always, always, always. That's 2x sub k plus 1. So if we substitute our x sub k in here, we get that, if f of x is really just 2x plus 1, then f of x sub k is 2x sub k plus 1. So when we substitute what x sub k is, we get 2 times 1 plus 2k over n plus 1. So what we're doing here is we're substituting this expression in here. And that would give us the f of x sub k for the Riemann sum. So our final answer would be the limit as n increases without bound of the summation from k equals 1 to n, and all of them begin with this, of f of x sub k, which is 2 plus 1 plus 2k over n, 2 times 1 plus 2k over n, plus 1 in brackets times delta x, which is 2 over n. And that would be my Riemann sum. All right, let's do C together. In C, A is -2 and B is 0, right? A is always the lower limit of integration. So our delta x is 0 minus -2 over n. That's 2 over n. Our x sub k would be a, which is -2, plus k times 2 over n. So f of x sub k is just x sub k plus 3 squared. So that would give us negative 2 plus 2k over n plus 3 squared when we substitute this with this. And the limit of the Riemann sum would be the limit as n increases without bound of the summation from k equals 1 to n of negative 2 plus 2k over n plus 3 squared, that's our f of x sub k, times the delta x, which is 2 over n. Okay, and of course you can simplify this into 1 plus 2k over n squared. Notice that the a and b are invisible in the limit of the Riemann sum. That we will discuss in the next exercise. And let's do e together. So a here is 2, b is 3, delta x is, b is 5. So delta x is 5 minus 2 over n, that's 3 over n. Our x sub k would be a, that's 2, plus k delta x. So f of x sub k is x sub k to the fourth, which would give us this expression to the fourth. And the limit of the Riemann sum would be the limit as n increases without bound from this of the summation from k equals 1 to n of f of x sub k, which is 2 plus 3k over n to the fourth times delta x, which in this case is 3 over n. Okay, pause the video and try problems B and D. Okay, let's go over B and D. A is 2, B is 4. So our delta x here is 2 over n. And our x sub k would be a, which is 2, plus k times 2 over n. Our f of x sub k would be 3x sub k squared minus 1. So that's 3 times 2 plus 2k over n squared minus 1. And the answer would be the limit as n increases without bound of the summation from k equals 1 to n of, in parentheses, 3 in parentheses, 2 plus 2k over n squared minus 1, close brackets, times 2 over n. And finally, for D, A is 0, B is pi, our delta x is pi over n, our x sub k here would be 0 plus k times pi over n. F of x sub k would be sine of x sub k. So in this case, it would be sine of pi over n. And the limit of the Riemann sum, sine of k times pi over n, excuse me. Forgot the k here. So it would be the limit as n increases without bound of the summation from k equals 1 to n of the sine of k pi over n times pi over n. And of course, this is the angle. Okay. All right, that takes care of translating a definite integral into the limit of a Riemann sum. Now, going the other way is more complicated because if we look at the problems above, x sub k always has k's and n's in it. Let's look at our x sub k's. I'm going to highlight this in orange. X sub k always has k's and n's in it. Okay, so it all stems from the x sub k. So the f of x sub k is after the sigma symbol. So if we take a look at these limits of Riemann sums, the x sub k's are the parts that have the k and n alone. And we could add a number, because remember, x sub k is a plus k delta x. This is a number, and this is always a number divided by n, right? This number is really b minus a. That's what's going to help us get our A and B. So if we look at all the problems, let's highlight just the part that has the K's and the N's. If we look at this one, this part has an A plus K times something over N. This part has an A plus K times something over N, and so forth. This would be our x sub k, and this part would be our x sub k. Is there an E? Yeah. And this part would be our x sub k. So what makes this trickier and more confusing is that we ignore all the operations on the outside and we look for a number plus k times something over n. So if x sub k is, and I'm going to write it as 2 plus k times 3 over n, so that I'm really separating the delta x. It looks like in this problem that delta x is 3 over n, right? I mean, it has to be. But the 3 represents the b minus a. So we could say that b minus a is 3. So the limits of integration are not explicitly given. We have to figure them out. So if we could figure out what a is, then we could figure out what b is. But in our problem, a seems to be 2, right? Because if this is our delta x, this is our a. So if a is 2, that would make b equal to 5, right? So the limits of integration for this problem are from 2 to 5. So that took a little bit of analysis. Now that we've got the limits of integration out of the way, and we know that this is really our delta x, which we could have found immediately, right? This would be our delta x, and this would be our delta x, and this would be our delta x, right? So the delta x is factored out, which we could have found in the first place, but we also found it from the x sub k piece. We have to figure out what f of x sub k is. So f of x sub k is whatever's going outside. The operation's going outside of x sub k. So if this is x sub k, this whole piece is x sub k, it looks like f of x sub k is 3 times x sub k minus 8. And that is our function, 3x minus 8. And that would be the definite integral that would represent it. Let's try C. Let's do D together. In D, all right, we know our delta x is, okay, so delta x here is pi over 6n. But I could rewrite this as pi over 6 divided by n, so it's in the format of the b minus a over n, which implies that b minus a must equal pi over 6. All right. Now, our x sub k is, I could put a 0 plus, okay, now it's k pi over 6n, which is, well, I'll write it this way, k pi over 6n. We write it as 0 plus k times pi over 6 over n. All right, which we wrote to be consistent with the right endpoint in the kth subinterval. All right, so since a here seems to be 0, because once we know what x sub k is, we know what a is, if a is 0 and b minus a is pi over 6, then b must be pi over 6. So our limits of integration are 0 to pi over 6. And what's happening to x sub k is that we put a cosine in front of it. So it's just cosine x with respect to x. And that's our integral. Okay, so now I'd like you to pause this video and try problems B, C, and E by yourselves. In problem B, delta x is 5 over n, which, oh, excuse me, I just wrote this wrong. 5 over n. So I'm going to jump and say that b minus a is 5. X sub k will rewrite as negative 2 plus k times 5 over n. It's in the correct format. That means a is negative 2. So if b minus a is 5 and a is negative 2, it looks like b has to be 3. Okay, so our limits of integration are from negative 2 to 3. And what's happening to x sub k is that we're multiplying it by 5 and subtracting 1. And that's our definite integral. In the next one, C, delta x is 2 over n. So b minus a is 2. X sub k is negative 2 plus k times 2 over n, which implies that a is negative 2. And again, if a is negative 2 and b minus negative 2 is 2, that means b is 0. So our limits of integration are from negative 2 to 0, and the integrand should be 3x plus 4 dx. And finally, for the last one, delta x is 2 over n, which means b minus a is 2. X sub k is 3 plus k times 2 over n, so a is 3. That means that b must be 5. Our limits of integration are 3 to 5, and the operation that's going on here is the square root of x sub k dx. And that completes the second part of the lesson. Now, sometimes the delta x is factored into the f of x sub k and distributed. For instance, in number 4, we have to factor out a delta x. 1 over n seems to be a very, very popular delta x, but we really have to be careful. And if we proceed in the same way, where delta x is 1 over n, we would get this definite integral. Okay, I'll leave that up to you. So let's do a together and see how we could rewrite that as a definite integral. So let's factor out a 1 over n. If we factor out a 1 over n like we did above, okay, that would be the first thing I'd factor out. I'd leave the square root of k there, but to get n to the 3 halves, if we multiply by n to the 2 halves, I need to multiply by n to the 1 half. So this is the square root of n. So going through a similar analysis, delta x is 1 over n, b minus a is 1, x sub k is really 0 plus k over n, because what's going on the outside is a square root. So if a is 0, b is 1, and the definite integral is the definite integral from 0 to 1 of the square root of x dx. Now, b is trickier, because in b, if we factor out the 1 over n, and the Riemann sum is written out, so we could rewrite this as the limit of 1 plus 4 plus 9 plus plus n squared, all divided by n squared, if we're going to factor out a 1 over n, right? And this Riemann sum can be abbreviated as the limit as n increases without bound of the summation from k equals 1 to n. And what are we adding? Things in the form of k squared over n squared times 1 over n, which again can be written as the limit as n increases without bound of the summation from k equals 1 to n of k over n squared times 1 over n. And using a similar analysis as above, where delta x is 1 over n, the definite integral would be the definite integral from 0 to 1 of x squared dx. All right, so pause the video and try C and D. All right, let's do C together. So in C, the 1 over n is already factored out. So this is our delta x. So b minus a is equal to 1, okay? And we could rewrite this as the limit as n increases without bound of the summation of from k equals 1 to n of things that look like 2 times k over n to the 2/3 times 1 over n, right? Because that's what we're summing up. All right. Now, if we look at this very carefully, we could go through the same analysis where x sub k is really 0 plus k times 1 over n. A is 0, which means b is 1. And what's going on the outside is that we are doubling x and taking it to the 2/3 dx. So the correct choice is A. And for the last one, which I again would take this as my delta x. And if I equate this to b minus a over n here is given. It's 25. So b minus a is 2. All right. And if we try to rewrite this in sigma notation, we get, all right, so let's see how we could rewrite this. So we get the limit as n increases without bound of the summation from k equals 1 to n, but here n happened to be 25, but I'm going to leave that out, of 2 over n times creatures that look like this, the square root of twice k, because they're even, divided by n. Okay, all right, because notice that what varies here are the numerators, and they're always doubled. Now, n here happened to be 25, but we're generalizing here. So so here, if x sub k is 0 plus k times 2 over n, which is consistent with our analysis, then a is 0, which would make b equal to 2. So the limits of integration are 0 to 2, so that knocks out 2 choices right there. But what's going on? We are square rooting x sub k. So the definite integral would be from 0 to 2 of the square root of x dx. All right, that one was a hard one. That one, I admit, was very hard. The 2/25 could throw you off, but just go with it, because sometimes they give us a variable for n. And if we ever have to write a picture into a definite integral as a limit, well, first, this represents the area under the curve from 1 to 4. So the definite integral is easy. The delta x is b minus a over n, which gives us 3 over n, since 4 minus 1 is 3. So our x sub k would be 1 plus k times 3 over n, and f of x sub k says double, then square root the x sub k, add 1 to it, okay, because this is f of x sub k. Remember, this whole thing is f of x sub k. So as the limit of a Riemann sum, this is the limit as n increases without bound of the summation from k equals 1 to infinity of 2 times the square root of 1 plus 3k over n plus 1, close parentheses, times delta x, which happens to be 3 over n. And this would be the limit of the Riemann sum represented by that picture. Okay, so I think that takes care of the lesson. I encourage you to try the others and check with me. All right, have a wonderful day, and I hope you found this helpful. Bye, everyone.